Hello everybody and welcome once again to the next module of NPTEL online certification course on microelectronics devices to circuits. Today's lecture will be on multistage and differential amplifiers. We have studied in our previous few modules about a single stage amplifier, which primarily means that if I have a simple common source amplifier, be it a MOS or a BJT, and I give an input signal which is basically a small signal ensuring that my devices are in the linear region of operation, then my output voltage will be undistorted without any nonlinear distortions available to it, and therefore, the gain will be almost independent of the input voltage. But a single stage amplifier, as you can always understand, will give you a gain which is quite small, right. It is the order of few tens, a few hundred, or maybe something like that. When you want a very large gain out of some particular for a particular operation, you either require a differential amplifier or even a multistage amplifier. So, what we try to do is that in the first half of the lecture, we will be looking into the concept of differential amplifier, and we will also look into the fact that using a single stage amplifier and by cascading it properly or adding stages to it properly, how can I make my gain high. One more important property of differential amplifier which was not there in a single stage amplifier is its capability of rejection of noise, which means that unlike single stage amplifier which amplifies both signal as well as noise, differential amplifier has got a capability of blocking the noise and enhancing the signal, right. So, signal to noise ratio sort of, if you want to take that as a parameter, will be quite high in front of a differential amplifier. So, with this basic knowledge or with this basic background, so the outline of the present course module is we will first of all look into a BJT differential amplifier under which we will look into its basic operation of the device. We will also understand what is the input common mode range with us, then large signal operation of the device, and then we will see that if we have an emitter resistance, how does the output transfer characteristics change, and then we will look into small signal characteristics. We will also look into differential half circuits, CMRR we will which is basically common mode rejection ratio, and then we will look at common mode input resistance, and then we will finally have a look into multi-stage amplifiers and two stage op amp as an example, and then we will recapitulate, right. So, these two, the last two we will be dealing in a much more detailed manner in subsequent slides or subsequent lectures, but today's topic will be more concentrated on differential amplifiers, right. So, let us first look at a differential amplifier, and to go ahead let me give you one brief insight. If you remember from your very basic device physics courses that if you have a BJT which is basically an NPN, or you will have PNP, right. This is emitter, base and junction for the base and collector, and therefore, if you want the device to be operating in the saturation region or in the triode region, you require the emitter base junction to be forward biased, right, and collector base junction should be reversed biased. If you want it to be in cutoff, then emitter base as well as collector base both should be reversed biased, right. I hope you have understood these points. If you want to work it in the active region of operation, then maybe emitter base and both collector base should be forward biased. This is your saturation region of operation, right. So, typically we want to keep this is where we define the bin on state and we get better idea, right. So, please understand, when you want to move the device BJT from a saturated state to non-saturated state, you spend large amount of time in switching, because the charges in the base has to be removed or flushed out before the next cycle starts. So, the time taken is very important. We will see in a differential amplifier that we do not like the devices to go into saturation region, and that is the beauty of the whole thing, that it gives you a much better gain, and not only gain, it gives you a much faster switching speeds. We will discuss one by one as we move along, but let us look at the first of all at a basic differential BJT differential amplifier, which is something in front of you which you can see here, right. This is a basic BJT differential amplifier in which we have got two transistors Q1 and Q2. We are assuming that Q1 and Q2 are perfectly symmetrical in the sense that they have exactly the same profile, they will give you the same amount of collector current for the same amount of base emitter bias, and so on and so forth. That is the meaning of Q1 and Q2 being symmetrical, right. And their VBE is, since it is silicon, we assume it to be 0.7 volts, because it is a silicon junction which we are assuming. We also have obviously a load resistance RC of the order of few ohms or kilo ohms. We have a plus VCC here, which is basically the power supply, and these two Q1 and Q2 are fed by a current source which is I, which as you can see here. And this current source I is basically a current source which is basically is considered to be an ideal current source, and therefore, if you look at the impedance at this point, Z will be obviously infinity, right, for ideal current source, which means that at this point it is the impedance looking at this point is particularly infinitely large, and whatever current flows through Q1 and Q2, if you add the currents, you will always get the total current to be equals to I. So what I get is that IE1 plus IE2 will always be equals to I, capital I. So this constraint always holds good, that the total current flowing through the left arm, which is this one, and the right arm, which is this one, will always be there. If you want to find out the value of VC1 and VC2, well, it is very simple. VC1 will be equals to VCC minus ICRC, right, because this is the voltage drop which you see, right, this is the minus ICRC, plus there will be also VCE SAT, which will be coming because of this one, for the device to be saturation, if provided I allow Q1 and Q2 to go into saturation. We will see that we will not allow it to do that, but these are the few constraints which one has to work upon, right, that the total current will be always fixed to I, and we are having VBE equals to 0.7, which is the cut in voltage for an NPN. We also assume that Q1 and Q2 are perfectly symmetrical in nature. With this knowledge, we also say that now we apply a voltage VB1 on the base side of Q1 and VB2 on the base side of Q2, right. If we assume that these two are correct, then what we can safely say is something like this, that we can say that that the collector current IC1 and IC2, which is the current flowing through the two collector arms of these networks, are also equal, provided VB1 is equals to VB2, right. So if I assume that VB1 equals to VB2, VB1 equals to VB2, we will see that mathematically later on, then if the same bias is there, everything else is same, IC1 will be equals to IC2, right. So this is the basic differential amplifier this thing diagram. Let me see what happens if we apply the same potential to the base of Q1 and Q2. So what I have done, I have simply applied a positive bias here, and the same potential is applied to the base terminal of Q2, and this is basically known as a common mode VCM. VCM is referred to as a common mode voltage, right. I will explain all these things later on, but at this stage just assume it to be common mode voltage. As the name suggests, this is the voltage which is common to both the arms, right. So you will ask me, why do you require it? Well, see, you initially, as I discussed with you earlier also, that you want this Q1 and Q2 to be in the region where you can actually achieve an amplification, right. So you require a DC bias from an external world, right, a DC bias which will fix this device into certain regions of operation where it can do an amplification. Then superimposed on that, you will have an AC signal being available to you. So these basically are a DC signal which you are giving, assuming at this stage what I am saying is correct, and under such a criteria let us see what happens. If I assume that I am giving VB1 equals to VB2 equals to VCM, the common mode signal, right. So I get VCM here, obviously this will give you a potential drop of 0.7, fine, and therefore the potential at this particular point will be VCM minus 0.7. So you have applied a potential DC bias here which is VCM, a 0.7 voltage drops takes place here. So at this point the value of the voltage will be VCM minus 0.7, right. So which means that both the devices Q1 and Q2 will be in on state provided VCM is greater than 0.7, fine. So if my VCM is greater than 0.7 volts, I would expect to see that both the devices will be in on state, right. So they will be on. When they are on, they will be carrying, since both of them are on equally, they will be carrying equal currents. So, therefore, if total current is basically equals to I, Q1 will carry I by 2, right, and Q2 will also carry I by 2. So, half the current will be flowing through the left arm and half the current will be flowing through right arm, and therefore, if you want to find out the current through this collector, remember if you are from your basic semiconductor courses, is that IC will be equals to alpha times IE. So, if your IE is equals to I by 2, I get IC equals to alpha times I by 2. So, IC is equals to alpha I by 2. So, therefore, as I discussed with you that VCC or output V out will be equals to VCC minus IC times RC, right. So, I get VCC minus IC is nothing but alpha I by 2 into RC. This is equals to V0, right. Now, you see, since it is perfectly symmetrical, this output voltage and this output voltage are exactly equals to each other. So, if you want to find out the differential of that, means if you subtract V out 1 minus V out 2, V out 1 minus V out 1 minus V out 2, automatically I will get a 0 volt, which means that it is very important stage, that any bias, equal bias given, or DC bias equal bias given to the two base of a symmetric differential amplifier, the output will always be equals to 0, right. So, DC bias and equal biases to both the arms does not give you a differential output voltage. Now, with this knowledge or with this idea, let me move forward and maybe show it to something else, that now what I do is I make a small change, that at Q2 I ground it, base of Q2 is grounded and my base of Q1 is given 0.7 volts. So, what will happen is, so this Q1 will have this again 0.7 volt here. So, 1 minus 0.7 you will achieve a 0.3 volt here, right. Now, if you give a base which is grounded, so base to emitter junction will be just 0.3 now, because this is 0 and this is plus 0.3. Please understand this is an NPN transistor. So, you are reverse biasing your emitter base junction, right, and therefore, Q2 will be basically cut off and Q1 will be on. I hope you agree with this point, that Q1 will be on and Q2 will be off, which means that Q1 will be responsible for biasing all the currents through it onto IC, fine. And therefore, as you can see here, if again by the previous statement which I gave you, V out will be equals to VCC minus IC RC. Now, if you see IC for the right arm Q2, IC equals to 0, so V out will be equals to VCC, and for the left arm it is VCC minus alpha by 2, it will not be alpha by 2, it will be alpha I RC, see VCC minus alpha I RC, fine. Now, if you find the difference between this and this, what the answer you will get is alpha I RC, fine, which means that if I give a difference voltage of plus 1 volt between the left arm and right arm, I get a output which is basically a DC output and is given by alpha I in times RC. Alpha is very close to 1, so I can approximately this to be as equals to I times RC, where I is the current flowing through the device. This is with the assumption that Q2 is perfectly off and Q1 is perfectly on, and all the current is routed through Q1, all the current of this current source is routed through Q1. So, this is the basic assumption is there. Now, so Q1 and Q2 are matched, I am assuming this to be true, right. Now, let me do one small thing and let me make a small change once again. With this, let me say that now, let me say my Q2 was grounded, right, but my Q1 I have given a minus 1 volt here, which means that if this is minus 1 volt here and if this is grounded, right, assuming this there is a potential drop here, I will get 0.7 minus 0.7 volts here. Minus 0.7 primarily means that this will be 0 bias, between this and this it will be 0 bias. So, what it will happen is that Q2 will be now on and Q1 will be off, right. So, understand the relationship, I am going for both the positive swing and the negative swing in my input. When I did a positive swing, my Q1 was on and Q2 was off with Q2 grounded. With my negative swing, of course Q1 will go off and Q2 will go on. Why? Because why Q1 is going to off? Because you are reverse biasing the emitter base junction and therefore Q1 goes to off state. But then this ensures that Q2 goes to an on state because minimum 0.7 volt is already there between the emitter base junction, and therefore it will be an on state, and therefore the reverse will happen, that my V out 1 will be equals to VCC and V out 2 will be equals to VCC minus alpha times IC, and therefore the output will be actually equals to minus alpha IRC. Assuming alpha to be approximately equals to 1, I get output to be equals to IRC. Let us see, so with this basic knowledge, what things we have been able to found out. We have been able to recapitulate or find out that if same voltage is given to the two base of the inverter BJT, the output will be always equals to 0, right. Therefore, what does the differential amplifier do? It tries to sense the difference between the two signals and then tries to amplify it, right. So, that is the reason it is known as a differential amplifier. So, if you look at the collector voltage, it is VCC, right, minus IC. So, it is alpha I by 2 into RC, provided both the devices are on, I get minus alpha by 2 alpha I by 2 into RC, which VCC minus alpha RC. With this knowledge or with this basic idea, let me therefore move on. So, as I discussed with you in the first case, Q2 will be off and therefore VC1 will be equals to VCC minus alpha I times RC, and VB1 when it is plus 1 volt, Q1 will be on and then VC2 will be equals to VCC. So, whichever the transistor is off, the output will be latched to VCC, and whichever transistor is on, the output will be latched to VCC minus alpha RC. In case 2, when you get VB1 is equals to minus 1 volt, in that case Q2 will be on, as I discussed with you, and therefore Q1 will be off. Q1 off implies that VC1 will be equals to VCC, and Q2 on implies that VC2 will be equals to VCC minus alpha I RC. So, all the current is routed through Q2 now. So, there are two cases across which the differential amplifier to work. Therefore, just see this point which I am shading here, that to use the differential amplifier, BJT differential amplifier as a linear amplifier means that the gain is independent of the input voltage, a fixed gain is available to me. We have to apply a very small differential signal of the order of few millivolts, right. Typically generally it is approximately 3 to 4 VT, we say. If the difference is this much, we will expect to see a change. 3 to 4 VT is approximately 75 to 100 millivolt difference should be there. VT is thermal equivalent voltage, which is approximately equals to at 300 Kelvin. This is we have already discussed this point, is known as thermal equivalent voltage, which means that minimum difference of 3 to 4 VT should be there for the switching or cutoff and switching to be proper. Now, therefore, the current through the transistors, the second point, will be I by 2 plus delta I and then I by 2 minus delta I. You understand the reason why it is, in one case it is minus, one case it is plus, and the reason is something like this, that assuming that as I discussed with you in the previous slides, let us suppose, let me just explain to you here, right, I will explain here, okay. Let me explain to you. Now, therefore, if I give in one case, if I give a base voltage which is higher, in another case I reduce the base voltage, then the current here will be larger and on the right hand side it will be smaller. So, I will just explain to you what I am trying to say. Let us suppose that I have got two arms here, right, and these two arms are going on here. In this arm I increase the base voltage VB, and in this arm I reduce the base voltage VB. So, if I increase it, the current becomes larger, right, the current increases. As the current increases, this voltage will drop down here. Similarly, when the base voltage reduces, the current reduces, and therefore, the voltage at this point actually increases. So, if I therefore make my base voltage, make it a differential base voltage, the current will be also differential in both the arms, and therefore, the voltage will also be differential in both the arms. That is what I am trying to say in the second statement here. The second statement that delta I and plus delta I minus delta I. So, in one case when the base voltage is increased, there will be an increase in the current plus delta I, and another current where there is a decrease, there will be a change in the value of current. But please understand, this delta I will always be same for both the arms, because if you add these two together I should get I. So, I by 2, right, plus delta I plus I by 2 minus delta I. If you see, this cancels off, and if you add these two I get I, which is the basic emitter current from the current source. So, I am not validating that basic principle, right, and that is the reason this is this thing. And therefore, if you want to take the output, you will get 2 times alpha delta I by RC, right. It will be 2 times alpha times delta I into RC. Why will you get 2 times alpha? The reason being, you get when you subtract the 2 together, I get, so if you subtract, say for example the current is I by 2 plus delta I. So, if you add those two, subtract the 2, I get I by 2 cancels out, and I get 2 delta I coming into picture. So, I get 2 delta I primary means that 2 times alpha times RC times, right, I get delta I, which is basically I here. So, I get this much delta I to be this much. So, I get this much as the current. So, which means that output voltage difference will be higher provided the current difference is also higher, right. Alpha is typically very close to 1, so that does not play a major role. So, delta I, higher the delta I value, larger will be the differential voltage output difference between the two. Now, let us see what is the allowable common mode voltage. So, the initial voltage, the DC voltage which I am giving to Q1 and Q2 before actually inserting a AC bias superimposing over it, let us see till what point VCM is allowed, right. Now, the allowable, as you can see, the allowable range of VCM common mode voltage is determined at the upper end by Q1 and Q2, leaving the active mode and entering into saturation mode. So, what I ensure is that both Q1 and Q2 should be in the active mode, and from active it should go back to cutoff, and my higher limit of VCM should be such that it does not allow you to go into saturation. So, I am sitting somewhere in the edge of my active region. Please understand this very carefully, that if you remember from your basic when we are discussing the BJT NPN transistors, we saw this to be as the saturation region. So, this was my active, right, this was saturation region, and this was my cutoff, this is cutoff, below this is cutoff. So, if you are biasing somewhere here, then you don't bias it very close to saturation region, keep it very much in the active region, because you want amplification to be there. But the highest value of common mode voltage which you can put is basically somewhere here, right, and the lowest value is somewhere here. So, the highest value is very near to saturation, and the very lowest value is near cutoff, but you do not keep it there, because then small change in VCM will result in the device going into saturation and thereby reducing your speed, or going to cutoff and thereby giving you a erroneous output result. So, keep it in the middle to find out. That is what I was saying, the lower end of the VCM range is determined by the need to provide a certain minimum voltage across the current source to ensure the operation. So, let us see what is VC max. VC max typically is the collector voltage which you give plus 0.4, which is nothing but VCC minus alpha into I by 2 into RC plus RC. So, this VC is nothing but this whole thing, right, and VCC minus alpha into I by 2 RC plus 0.4 approximately, and VC min is equals to minus VEE plus VCS plus VBE. Why? Please understand why is it like that. If you go back to your previous slide, you see you have biased this with minus VEE, right, and this is your base to emitter voltage VBE. So, what was written here? It was written as minus VEE, right. So, minus so I will write down, sorry, minus so it is minus VEE plus plus VBE, right, plus VBE plus VCS, right. So, this minus VE is, and I am saying this to be as approximately the value of your VCE minimum value. Why? Because any voltage, see, so for the device to be in on state, I require minimum VBE to be potential given to the base side, otherwise it will go into off state. So, assuming that your Q1 is in the on state, I have to give a minimum voltage of 0.7 VBE onto the Q point. So, that takes care of this one, right. Is it okay? What is VEE? VEE is this potential. So, minimum this potential has to be there in order. So, because this potential is appearing. So, this is basically your VEE, and this potential is appearing somewhere at the edge of your current source here, right. So, the minimum amount of DC bias. So, because if you do not give this much amount, this will actually reverse bias your sorry, it will forward bias your Q1 every time, and therefore, you require minus VEE as one of the point, and VCS is basically the collector to source potential, which you need to add to VBE in order to ensure that the device is in the on state. So, the requirement therefore is that for the VC max, common mode max is given by this, and common mode min is given by this, right. So, if your VCC is typically around 3 volts or 4 volts or 5 volts, then you can see what is the value of VCM max. So, higher the value of VCC, more you can go for VC max without entering into the saturation region of operation. And the critical part is that we do not allow it to enter into saturation region, because then it compromises on the speed of the device, right. Let us look at the therefore we have understood therefore the small signal model, not the small signal model, the basic operation. So, what I will do is I will give a differential voltage here. If therefore, I will get a 180 degree phase shifted signal between Q1 and Q2, I will get an output which is 180 degree phase shifted. If you therefore take the difference of the two collector voltages, the output voltage will be twice, and therefore, I will get a differential of twice approximately. Now, if obviously if the voltage at the emitter is given by VBE, and therefore, assuming that there is no early effect, then I can safely write down the emitter voltage IE to be equals to IS by alpha into e to the power VB1 minus VE by VT, my basic semiconductor equation, and VE2 equals to IS by alpha into e to the power VB2 minus VE. Now, if you add, and therefore, this equation, if you do like this manipulation, I get this into consideration. And if I do some IE, so the IE2 by IE1 plus IE2 I get this, I will also get IE1 by IE1 plus IE2 equals to this, right. Now, you see, so IE1 by IE2 this will cancel off, right, and this will cancel off, this will cancel off, sorry, this will remain there, and therefore, IE1 by IE2 is equals to e to the power VB1 minus VB2 by VT, and there, even without knowing the physics of the device, you can appreciate that higher this difference between the base voltages, right, more will be the ratio this one. So, which means that if VB1 is much larger as compared to VB2, right, everything else remaining the same, IE1 will obviously be much larger as compared to IE2, and therefore, IC1 will also be much larger as compared to IC2. So, that is the bottleneck, or that is the sort of the whole crux of the whole issue, that I need to make one side base voltage much larger as compared to another side. Now, we also know that IE1 and plus IE2 will be always equals to I, you see this one, and we refer to VBI minus VB2 as VID. ID means input difference between the two. Why we are saying input difference between the two? Because you see this potential is always constant, right. I will just come back to the previous slide and you will explain. This potential is always common to the both the emitters of Q1 and Q2. So, let me name it as X, then Vx is common to both Q1 and Q2. Therefore, since this is common to both, I just need to find out the difference between this voltage and this voltage, that is all. So, that is the reason I am referring to this as VB1 minus VB2, right. I am forgetting the common node, because unnecessarily complicate the matters, and therefore, I refer VB1 minus VB2 equals to VID. Therefore, I can write down IE, right, IE1 to be equals to I, the IE1 to be, so this is basically your I. So, this is I, this I can take it in the numerator, and I get I e to 1 plus e to the power VB1 minus VB2 is VID. So, VID minus VID by V2, and I2 equals to I upon 1 plus VID by E2 exponential plus VID2, right. So, one has got a negative sign and another has got as a positive sign. So, these are the emitter currents which are available to us, right, and if you want to just find out the collector current, you multiply this with alpha. So, I C1 will be equals to alpha times I upon 1 plus exponential minus VID by VT, right, and IC2 will be equals to alpha I upon 1 plus exponential VID by VT, fine. Okay. Now, with this knowledge which you have gained till now, right, let me just therefore give you a small idea about the transfer characteristics. Now, on the y axis you will see it is basically the normalized collector current, which means that the collector current normalized with respect to the total current which is available to us, and therefore, the maximum I can go is 1. And on the x axis we have VID by VT. VID is basically the difference voltage of the base. So, VID is, as I discussed with you, is basically VB1 minus VB2, right. So, if you divide that by VT thermal equivalent voltage, this is what I get. This is the point 0 where VBI1 equals to VBI2, right, and as you move to the left or right, let us see how it works out. As you move to the, let us suppose left, right, as you move to the left, or let us say we are moving to the right, that is more easy to understand. It primarily means that my moving to the right means this is becoming more and more positive, which means that VB1 is becoming more and more higher as compared to, so VB1 is getting higher and higher as compared to VB2, which therefore means that the Q2 is in the off state and Q1 is in the on state. When Q2 is in the off state, obviously when Q1 in the on state, I will get on current available here at this particular point, right, and therefore, if you look very carefully that as you can see, the collector current which is flowing now, when you make your VID very large, right, this is very large as compared to VB2, right. So, Q1 is in the on state, right, and Q1 is in the on state. Q1 is in the on state primarily meaning that you have a large collector current available to it, and therefore, you see you have large collector current, IC1 by I is the large collector current, whereas since already Q2 is in switched off mode, the current goes to 0, and you can see the current goes to 0. So, this is the Q2 current and this is Q1 current, this one is Q1 current and this is Q2 current. Similarly, if we go to extreme left somewhere here, then VB2 will be much larger as compared to VB1, and therefore, your second Q2 will be on having a large current and Q1 will be off. So, this you see is a perfectly symmetrical sort of a butterfly available with you, this is perfectly symmetrical. Somewhere in the middle where you will have VB1 equals to VB2, which means that VID equals to 0, you automatically get a place where the current changes drastically with respect to VID. So, we will start from here in the next slide, in our next discussion we will see how it works out, and we will discuss from the linear region of operation how we can move ahead and give you the value of CMRR and give you the value of the differential mode common signal, right. Thank you, thanks a lot.